Last video, with the help of the Fokker D8, we motivated why, when designing structures, we should be concerned with the response to loading. In your early mechanics classes, you dealt with rigid bodies, cannonballs fired at angle theta and speed v0, blocks sliding down ramps of height h, and pendulums with period t oscillating back and forth. The underlying assumption in all of these problems is that the object in question is completely rigid. It doesn't deform or squish or lengthen due to the forces exerted on it. However, this is an approximation. As in the words of world-famous aeroelastician Earl Dowell, there is no such thing as a rigid body. All bodies, when forces are applied to them, deform. Putting a heavy coat on a hanger will cause it to bow. Hitting a baseball will cause that ball to compress and squish. And whenever you play with some Play-Doh, it always manages to deform around your finger. Although it is much mathematically easier to treat a body as rigid, sometimes this approximation is not appropriate. Many times, it's crucial to consider how these bodies deform. For example, in aeroelasticity, the study of elastic or deformable interactions between aerospace structures and their environment. Let's go over some of the basics of elasticity, the study of deformable bodies. Suppose we had a bar of aluminum 1 meter long, and on either end, we applied a force of magnitude F. Because we are pulling on the bar from both ends, this is known as a tensile force, and so we would say that the member is in tension. I want to look at a single cross-section of the bar. Notice, just like the rest of this bar, this section must be in equilibrium. Thus, there are some internal forces that are equal and opposite to the applied tensile force. This internal response of this piece of the bar is known as stress, specifically normal stress, because it acts normal to the area cross-section. This normal stress is the force of internal response spread out across the entire cross-section. We do this because we would like to normalize the internal response force with respect to area. Therefore, the normal stress is equal to the force applied divided by the cross-sectional area of the beam. Now, let's say we flip the applied forces and try to compress the bar instead. We can see that the normal stresses would also flip. We would then say that the member is in compression. I mentioned that whenever forces are applied to a body, that body deforms. Axial loadings like compression and tension will cause the member to change length. Suppose our aluminum beam originally had a length L, and we applied some tensile forces to each side. Then the beam would lengthen to a new length of L prime. Note that the amount of deformation that I have indicated in the animation is unrealistic for, say, an aluminum beam. Typically, deformations are quite small for most metals. For example, if you had a 1 meter long piece of aluminum with a cross-section area of 1 square centimeter, and you wanted to stretch that aluminum beam by 1 millimeter, you would need to have more than 1,500 pounds of force to do so. Notice, for our aluminum beam, if we increase the force applied, say we doubled it, then the deformed length would also increase. Also, we could have compressed the beam instead. If we compress the beam, then the deformed length would be shorter than the original length. Remember, members will be shorter in compression and longer in tension. The amount of relative change in length divided by the original length due to some normal stress is known as the normal strain. Another way to think about the strain, given that it's dimensionless, is that it is the percent increase or decrease in original length due to an applied force. Note that normal strain is positive in tension and negative in compression. Here's a question you might have. For a given material, how much stress will cause a given amount of strain? We know that some materials are much less deformable than others. Scientists can answer this question through the use of stress-strain curves. In a tensile test, a sample of the material is taken, and a slowly increasing tensile stress is applied to the material, and the amount of strain is measured. For low values of stress, the stress-strain curve will be linear. At a certain stress, however, the linear relationship stops, and this is known as the yield stress. Eventually, as higher stresses are applied, the curve becomes more complicated, forming an arc that reaches a maximum at the ultimate strength of the material. Eventually, as even more stress is applied, the material fractures. Each material has a unique stress-strain curve, and lots of information can be extracted from them. For most engineering purposes, engineers look at this linear part of the graph, highlighted in green. It's known as the elastic region. Remember, if I were to apply stress to a material, the material would deform in some way. If that stress lies in the elastic region, when that stress is released, the material would deform right back to its original length. If the stress lies in the plastic region, when the stress is released, the member will not revert back to its original length. Because the elastic region of materials is much more predictable, almost all engineering applications ensure that their stresses will lie in this region for safety reasons. Hooke's law governs the behavior of materials in the elastic region. Hooke's law says that for almost any material, the normal strain changes linearly with the amount of normal stress. The coefficient of linearity, or the slope of the stress-strain curve, is known as Young's modulus, or the modulus of elasticity, and it has dimensions of force per area. E, physically, is the slope of the stress-strain curve, and it represents how resistive or stiff the material is to loads. Materials like aluminum that are stiffer have high moduli of elasticity, on the order of tens of gigapascals, whereas materials like rubber that are much more flexible have lower moduli, on the order of, say, 1 megapascal. However, there are other ways to apply forces to our member other than compressive or tensile loads. What if we applied a force to a beam like this, a shear force? We would expect the beam to have some responding stress, known as the shear stress. The average shear stress can be calculated by looking at the applied shear force over the cross-sectional area. To see what is going on, let's take a look at a small piece of material near the end of the beam. We know that there is a shear stress applied by some load on this element on the right. Because the beam, and thus all small elements, are in equilibrium, an internal shear stress on the left must be applied to balance the external stress. However, left in this configuration, the element would rotate because there's a net moment due to these shear stresses. We obviously know that the beam is not rotating, thus this implies that there must be two other internal stresses on our small element to prevent rotation. These stresses will cause our element to deform from a perfect square to a rhombus, given that pairs of stresses are pinching the corners of our element. The angles alpha and beta represent how much shear strain has occurred. The larger the angles, the larger the strain. And, as it turns out, luckily, in the linear region of shear stress, there's a Hooke's law for shear, where G is known as the shear modulus. G represents how resistive a material is to shear forces, and can be determined in a similar way to a tensile strength test. In this video, we have covered the very basics of the theory of elasticity, but there's a lot more to learn. Join us next time as we introduce the subject of torsion.